Good morning, students. So now today we are going to learn Biot-Savart law. This is a very important law in class 12, and it is actually containing a slightly complicated concept because it contains the cross product. And from my personal experience, I have already seen that many students find it difficulty to understand the direction of the cross products. And this difficulty actually gets its extremum when the students find those questions in exam, in board exam and any other competitive exams. So our goal is to tell what the law is, what the law describes, and what are the other forms of the same law which can be asked in different questions and different, and that will actually help us to solve the various numericals. So let us begin with that. So it is telling, first of all, the Biot-Savart law is telling when a current is flowing through a wire, a magnetic field, which is denoted as a vector B, is generated around the wire. Okay, and the it is the first time the law is giving us the quantification of the magnetic field in the sense that we can measure the magnetic field on the basis of the given parameters. Okay. So now we are going to draw a wire, and it can be curved or it can be straight line. So I'm drawing a curved wire, and it is carrying a current I in the sense that I am taking the current as uniform current. Okay, and we have to find the magnetic field at a distance r from the wire at any angle. So the position vector of this point is r vector, and we have to find the magnetic field at the point P. Okay, okay. So before going to describe the law, we have we are going to fix the direction first. The direction is telling that where the current direction is. So this is the current direction, right? So when the current is going up like this, then the right side of the wire, in the right side of the wire, all the magnetic field, the direction of the magnetic field is vertically downward, in the sense that it is pointing inward to the plane you are observing. So it is totally vertically, the magnetic field lines penetrating the plane of mobile phone or the screen you are watching, and it is pointing inward or vertically downward. And it is denoted by this cross symbol. It is showing that the magnetic field is vertically or vertically downward. Okay. So we have fixed the duration right now. See, and the left side of the wire, it is always a vertically inward. It is often denoted by dot, which is in circle dot you can say. So the direction is now fixed. So right side of the wire, when the current is going up in this manner, in the sense that it is moving along north direction. So in the right side, the magnetic field is vertically inward, and the left side is vertically upward. Yeah. So directions are now fixed. So now we are ready to give the law, to describe the law in mathematical form. So for that purpose, we have to find a small element, a line vector, small vector dl, along the direction of the current. So the sign, the vector, the direction of the vector is actually the direction of the current. Hmm? And we have to find the magnetic field at the point P, and obviously it is vertically downward. And just I encircle the magnetic field here. Since we are considering the particular line element dl, the magnetic field generated by this small element is dv say here. Okay, good. So according to Biot-Savart law, the dv is equal to mu naught by 4 pi I dl cross vector r by r cube. So this is Biot-Savart law. Okay, so this is a mathematical form of the Biot-Savart law. Yeah. Good. So there is no, so there is cross. We are not bothering about the cross product right now because the cross product is giving me the direction, and we have already fixed the direction from very beginning of this class. So we are not bothering about the cross product. We are just we have to remember which is the first vector in the cross product and which is the second vector in the cross product. That is the DL is coming first and R coming next. Vector R coming next, and that we have to remember. Okay, but we are not bothering about the direction coming from the cross product. We have already fixed the direction. We have already known the direction. Okay, what is mu naught? Like in the electric field, we have already seen that there is a quantity called epsilon naught. Epsilon naught is the permittivity of vacuum. Similarly, we are going to define another property of vacuum, which is a magnetic property of the vacuum. Is called the permeability. It is called magnetic permeability or simple permeability. What is its significance, physical significance? So let me write the physical significance. The physical significance of its significance is it gives the existence of the magnetic field in a okay in a medium. What does it mean? It is saying that if a medium has a permeability, then this medium has can contain or can hold the magnetic field created by the current. Like the permittivity gives the existence of the electric field in a medium. And the mu naught is giving or mu is giving the permeability or the existence of the magnetic field in a medium. It is saying that if a current is moving along in the medium, then always we have the magnetic field. If a medium is not having the permeability, that 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 signifies that the medium cannot hold the magnetic field, or that the magnetic field cannot be produced in the medium. Okay, so this is the physical significance of mu naught. So now I'm going to simplify this particular expression one step ahead. So I'm just writing that the r vector is r into r cap. We can write always a vector, any vector equal to the magnitude of the vector into its unit vector, and putting it the expression on the Biot-Savart law, that is the dv becomes mu I by 4 pi dl cross r cap by r cube. So one power will be gone of the r cube. It becomes 2, and it is mu naught I by 4 pi dl cross r cap by r square. So this is dV. So you can write the first expression and also you can write the second expression as your wish. It does not hamper anything. Okay. So there is a second expression, a second form of the Biot-Savart law. I'm not, I cannot call the second form because it is a simplification of the first one, right? So I'm putting the R into R. Yeah. So now our target is to find the magnetic field due to the total wire. So I'm going to integrate that dV. So it becomes B and mu naught by 4 pi is the constant is taken outside the current and that is I'm keeping the ideal vector r cap by r square. But before going to proceed, we have to know that there is a very important thing I have to mention here. Since the I is uniform, in the next step I can take I can bring I outside the integration. But if I is not uniform along the wire, we cannot bring I outside the integration, right? Because I varies with the length of the wire. So generally in the 99 percent cases, we will take the I uniform. That's why I am taking I outside the integration because I is constant here. So the final expression is for the total magnetic field is simple that dl cross r cap by r square. So is a assumption, a hidden assumption is here that I is uniform, which has already been taken from the very beginning. Okay. So this is the final expression of the, so this is a total magnetic field and we have to put the limit here, upper limit and lower limit to get the right expression or the final expression of the magnetic field due to whole wire. Okay, so we will see that how to put the limits and how to calculate in some cases. So there are two or three cases we have to apply the magnetic field, apply this integration to find the magnetic field due to whole wire. And we will see those things later. Okay. But before proceeding to this direction, so we have to express the magnetic field in terms of the other quantities, which is called the current density, that is J. Okay. And another another case we have to consider when the magnetic field due to a point due to motion of a point charge Q. Okay. So let us move to the first one. That is, we have to express the expression in terms of the current density. To get the current density, we have to consider the dimension of the wire properly in the sense that now we are considering it is a cylindrical wire and the current is moving through it along the uniform current is moving through it and it is uniform over the cross-sectional area and the cross-sectional area of the wire is taken as A and current is perpendicular to this area and we know the relation between the density of current density and current which is given by I equal to J dot A. But since the area vector and the J vector are along the same direction, okay, that's so the dot product. So here the angle, so J is parallel to the A vector. That means here the angle between them is zero. So it becomes simple AJ, right? So now we are going to put this expression in this here. uh, and to find the magnetic field due to the whole wire, so it becomes magnetic field B. So mu by 4 pi. So it becomes simple. So I'm taking I inside. So that is J A, well, into dl cross r cap by r square, and mu, and what is so now we are going to express all the things properly. So I'm writing dl again in the vector property as ja dl into unit vector along dl. So suppose this is dl, and along this direction I am taking a particular unit vector, say this unit vector, say l cap. So dl into l cap cross r cap by r square. But what is A into dl? A is the cross-sectional area and dl is the length. So this particular ADL is giving me the volume of this particular line element around the line element. So that is ADL is actually the volume, elementary volume, that is dV. So it becomes mu naught 4 pi J dV L cap R cap by R square. So that is, now what we are going to do, I multiply J with the L cap. Since the L cap has the same unit vector as J has, that means because the J has the same direction along the wire as JL, so that means so DL has the same direction of J. That means the same unit vector both have the same unit vector. So J L cap r cap by r square into dv. So I can write easily that is J L cap is J vector because both L cap is the same unit vector of along J. So that means the formula becomes mu J vector plus r cap by r square into dv. So this is another form of the Biot-Savart law in terms of the current density. So it can be asked in the exam to recognize that this is a Biot-Savart law, okay, when it is expressed in terms of the current density. Yeah. So there is a magnetic field, which is a function of vector r. Hmm. So this is mu I by mu naught by 4 pi integration j cross r cap by r square dv. dv is the volume element right now. Okay. So dv, I'm going to write it is simple ADL. A is the cross-sectional area of the wire. So this part is over. So please remember, unlike the previous case, this is actually the volume integration, not the line integration. Okay, it is not, this integration is not taking along the line. It is a volume integration. It is this particular integration is taken over the volume of the wire. That's why the current density is appeared in this picture, and we have already seen that how to write the current density in terms of the current or vice versa. Okay. So please remember this properly. So here it is a volume integration, not the line integration. It is appear to be line integration, but it is actually the volume integration here. And the third case is the when the magnetic field. So now we are going to consider the magnetic field due to a moving charge, moving point charge, I should say. There are many ways to express this, but I am going to express in my way. So suppose a point charge is moving, suppose that is the Q is moving along this direction with a velocity v, and we have to find the, okay, we have to find the magnetic field here. So this is R vector, that is theta say. Okay, so this is we have to express this here, the magnetic field, which is pointing again. Since the current, since the charge is moving upward, so we can assume the movement of the positive charge is giving me the current. Okay, and the magnetic field is now here. So at the point is P, right? It's clear. So this is very important thing. Good. So now we are going to assume in some dt. So we are going to consider a particular time interval, that is dt. The length, the distance, the distance this charge travels is simple v dt. The displacement is v, that is dl, and that's all. So now we are going to apply this. So yeah, and we are going to write this Biot-Savart Law. So dv is simple mu naught by 4 pi, okay? And we are going to write this mu naught I by dl cross r cap by r square. So now we are going to write everything. So mu is, so dv is I, and I'm writing dl in the place of dl, that is v dt cross r cap by r square by 4 pi. So mu naught 4 pi v cross r cap by r square is common. They are all constants. Okay. And that is I dt is remaining. So now we are going to integrate that. Integrate. So I'm going to integrate it. That is dv equal to vector b say. So mu naught by 4 pi vector v cross r cap by r square integration I dt, and integration I dt is the total charge. There is q here. So that is mu naught v cross r cap by 4 pi r square into q. Why I am telling this? Because we know that liquidity is the current, right? So we know that the liquidity is current and q is I dt integration, right? So that is why I am writing this place I dt as q, and which is the point, the total charge of the point charge, that is q. So the final expression of the magnetic field due to the motion of the point charge with the velocity v is mu naught by 4 pi q into v cross r cap by r square. So this is the final equation of the magnetic field of the point charge moving along this. Good. So that is the very important thing. So we have found the three expressions of the same magnetic field, and one is the basic definition of the magnetic field. So now we are going to summarize what we have already learned. So three expressions. One is the magnetic field due to whole wire carrying current, uniform current I. Okay. Second is, so this is the magnetic field due to uniform current at R. Second is This same expression is expressed in terms of the dimension of the wire, right? In the sense that I have brought the current density into picture. So it becomes a volume integration. So that is become J cross R cap by R square into dV. And third is the motion of a point charge. So it becomes B R vector, that is mu naught I by 4 pi. So sorry, we have already expressed the I in terms of charge, that is Q V cross R cap by R square. Fantastic. So that is the magnetic field B. So these three expressions we have to remember because any one of them can be asked in the MCQ, which are the even these questions were asked in previous year's questions. So what is the magnetic field? So these are the expressions of the magnetic field. Okay, good. So this is the complete theory of the Biot-Savart law. And then we will see what is the application of the Biot-Savart law. So I'm going to apply the Biot-Savart law for a simple case. The simple case is the derivation, one kind of a derivation you can say, that is the very easiest derivation to find the magnetic field at the center of a current carrying loop. So this is the expression we have to apply the magnetic we have to apply the Biot-Savart law to find it. It's a very very easy one. So first I am going to draw a circular loop, okay, and then we have to find the so suppose the current is flowing here and okay, so this is a center. We have to find the magnetic field at the center, and you can only see that this is the left side of the current, and that is why here the magnetic field is vertically upward, right? We've already decided when we are talking about the current, the left side is vertically upward and right side is vertically downward. So it is already left side to the current, and that's why it is a vertically upward magnetic field at the center. Okay, so now we are going to apply the Biot-Savart law and see the how to calculate the magnetic field with the proper giving the proper limit. So I am taking only the DL part here. DL is taken tangentially. So I am connecting this tangent, elementary tangent to the center. So that is the radius of the wire, say. So the radius is say R. Okay. So the distance is R, and the distance between the distance and DL, the angle is so the vector R. The angle between vector R and DL is 90 degree, right? It is obviously it is 90 degree because DL is tangent to the DL is along the tangent of this circle. Good. So dV, according to Biot-Savart law, is mu I by 4 pi r square dl plus r cap. R cap is this direction, and from this picture, it is easily visible that is r cap is perpendicular to dl. And since we have already decided what is the direction of the magnetic field, we are not bothering about the cross product right now. We are not bothering about the vector property of this Biot-Savart law because we have already decided the direction of the magnetic field, and therefore we are taking only the magnitude here. So dV is mu I by 4 pi r square. So cross product of A cross B, the mod of we know that is mod of A cross B is AB sin theta. So here we have to take the DL R cap sine 90 degree because they are perpendicular to each other. And the unit vector has magnitude 1 and sun angle is 1, so it becomes mu naught I by 4 pi r square. So that is dl. So total magnetic field at the center becomes the integration over dv, so mu I by 4 pi r square into that is integration of dl. But integration of dl, that means that is the total length of the circle, because we are considering the total wire. And since the line is closed, in the sense that the circle is closed line, that means we have to give a small designation of this integration to denote it is this is a closed line integration. And we know what is this result. It is, we are not bothering about this integration, the symbol of the integration also, but for this calculation purpose, I have given that. But we know the result. Result of this particular is the total length of the wire, that is simple 2 pi r. So pi pi cancel, r cancel, so it becomes mu I by 2r. So that is the magnetic field at the center of a circular loop. This is a very important and very small derivations, and we have already seen how to apply the Biot-Savart law to get the magnetic field for a particular in a particular purpose, right? So that is very important. For for next classes, so we will see the how to calculate the magnetic field for the other purposes and for the other cases. Okay.